So for my day job, I'm a professor at CU Boulder in the Department of Astrophysical and Planetary Sciences, and I research the formation and evolution of galaxies, so how do galaxies grow and evolve over cosmic time. And recently I've been doing a lot of work with the James Webb Space Telescope, which was launched a couple years ago, which is what I'm going to tell you about today. So I want to thank all of you for being just the most amazing and wonderful community. Tinkermill means a lot to me, and it's really exciting to be able to talk about science with all of you. And then also, all the work that I'm talking about is sponsored by either NASA or the NSF. So whether or not you thought you paid for this talk, you did. So out of like every $100 you pay on your taxes, something like 10 cents goes to NASA, and some extremely, extremely small portion of that pays my salary and the salaries of my really awesome group members. This is my undergrad. Let's see, my undergrad, my 3 grad students, and my 2 postdocs at CU. And all of us are really grateful that we get the opportunity to do science and that we get to ask these questions about how we came to be in the universe and what's out there around us. And so thank you so much for your support, both of me personally and then also of the work that we're doing more broadly. So I wanted to start just kind of like introducing what a galaxy even is. So I want all of you to imagine that you're standing outside on a dark night, and for the sake of argument, let's just say that there's no electric lights, so there's no light pollution, so you can perfectly see everything in the night sky. And also, let's just imagine that you're in the southern hemisphere. This is about something that it might look like. So this is the night sky as seen from the extremely creatively named Very Large Telescope, or VLT, which is in Chile. And so you can see a couple of different things in this picture. The first thing is the Very Large Telescope, which again, if you were before electric lights, you probably wouldn't see. The second thing is a whole ton of stars. So hopefully even in Boulder with the light pollution, or in Longmont, you can see a lot of stars in the night sky. So these are stars just like our sun, but outside of our solar system. And then also we can see the Milky Way. Has everybody here, like show of hands, have people actually seen the Milky Way? Yes?
Thank you, CE.
Yeah, thank you, CE. If you haven't yet, go to Rocky Mountain National Park with CE and he'll show it to you. So astronomers have known actually for a long time that the Milky Way is made out of individual distant stars. So it's basically just a bunch of stars and gas that's all sort of collected here. I'll show you a picture that'll explain that in more detail later. But we've known this actually, like the ancient Greeks had a lot of arguments about this. So this is a thing that Democritus was really excited about, is that the Milky Way is made out of individual stars. We proved it observationally. The Arabian astronomer Alhazen proved it in something like the year 1000 with parallax measurements of stars in the Milky Way to show that it's definitively outside the Earth's atmosphere. And then, of course, in the 1600s, we started getting telescopes and were able to actually observe that the Milky Way is made up of all of these distant stars. But does anybody see anything else in this picture other than the stars and that band of the Milky Way? Galaxies? Yes, the Magellanic Clouds. Oh gosh, I should have known that you guys were the exact right audience to get all of my questions right. So these 2 little things, these like fuzzy blobs here, this is why I said that I wanted you to imagine being in the southern hemisphere. These are the Magellanic Clouds. If you're in the northern hemisphere, you can maybe also see Andromeda as a very, very faint fuzzy smudge, sometimes in the northern sky. And again, astronomers had arguments about what these were for quite a long time, whether or not these were nebula, which are regions that are forming lots of young new stars, or whether these were these sort of island universes, which are things just like the Milky Way, but very far away. And it turns out that that second argument actually is the thing that won. So we built up this evidence that these Magellanic Clouds and Andromeda are other galaxies like the Milky Way, but very, very far away, so we can just see them as these very small little smudges in the night sky. And that was due a lot to the work of Edwin Hubble, who I'll mention later. So Edwin Hubble actually made distance measurements to both Andromeda and several other local spiral galaxies, helped a lot by pioneering techniques in measuring the brightness of objects from Henrietta Swan Leavitt and the team of they were called calculators, actually, at Harvard at the time. So a galaxy is a bunch of different components. So it's stars, like I said, like our own sun. Stellar remnants, so this is the stuff that gets left behind after stars die. So it's white dwarfs and neutron stars and black holes. There's also a black hole, a supermassive black hole, we think at the center of almost every galaxy. This is an actual picture of Sagittarius A star, which is the supermassive black hole at the center of our galaxy. It's really amazing that we were actually able to take this picture. The thing in the middle, so you can see it's black here, that's the actual black hole, and then this bright disk around it is the black hole eating a bunch of stuff, and the stuff that's falling into the black hole is glowing. So this gas that's around this black hole is like absolutely ripping. It's at like a couple of thousand kilometers per second that it's moving. So it's very, very bright. There's also a lot of gas and dust. So this is the stuff that young new stars form out of. And then also galaxies contain quite a bit of dark matter. We don't know what that is, so I didn't put a picture of it here. But there's a lot of it in galaxies. It's a very important component, as Vera Rubin discovered. And so out of these very simple building blocks, you get a huge diversity in what the observed properties of galaxies actually look like. So a lot of galaxies that we see in the local universe are these spiral galaxies shown here. So this is kind of what our Milky Way looks like. These spiral galaxies, sometimes they have bars, like this one here. These are images from the Hubble Space Telescope. They're kind of shaped like pancakes, so sometimes you see them edge on instead of face on, and this is why the Milky Way looks like a line, is that we're basically looking out through the thick direction of the pancake. And then there's also these elliptical galaxies, which are no longer actively forming new stars. They look extremely boring, but they are my favorite type of galaxies. They're the ones that I work on the most, so please, even though they don't have the beautiful arms, give them a little bit of love. And so the idea is that by studying all of these local galaxies, hopefully we can try and understand how these things got to be the way that they are. So how do galaxies develop these spiral structures? Why do they show this great diversity in properties? And effectively, by looking at these galaxies in the local universe, we're doing something like archaeology, right? We're looking at the sort of, the bones of these old galaxies that are around us in the local universe. But the really amazing thing about being an astronomer is that we don't just have to do the bit where we look at the local galaxies. We can actually go back and see the real live dinosaur. And so this is because of an effect called cosmological redshift. So light doesn't travel infinitely fast. It takes some amount of time to get from point A to point B. And so what this means is that if we are an astronomer looking at some galaxy with our telescope, if that galaxy is very close by, the light didn't take that long to travel from the galaxy to us. And so it means that we're seeing light that was emitted pretty recently in the past, and we're seeing that galaxy as it was pretty close to now. But if we look at a galaxy that's much further away, it takes a much longer time for that light to get to us. And so the light that we're seeing now was emitted much longer ago, and we're seeing that galaxy as it was much further in the past. And I want to pause here because this is like actually still my favorite part of my job, which is that we have a time machine, right? Like we actually literally have a time machine to watch how the universe is growing and evolving. And so all we have to do in order to use this time machine is look far away, and that's the same thing as looking back in time. So the further away we can look, the closer to the beginning of the universe we can see. And so the question is, can we actually use this in practice? Because of course, things end up being fainter if they're further away. So you can imagine if we take this galaxy and we put it further and further, it's like if you're standing further and further away from somebody shining a flashlight, at some point you're just not really going to see the light that they're shining in your direction because they're just too far away. And so the question is, are galaxies too far away for us to actually be able to see them? And for a long time, that was true. So with most of our ground-based telescopes, for most of history, we couldn't see galaxies that were beyond the quite local universe. And this was also true at the time when we launched the Hubble Space Telescope. So this Hubble is about a year older than I am, so it was launched in the very early 1990s. I don't know why you're laughing. I'm not that old. Like, Hubble's still working. I'm still working. It's fine. So if you took something like Andromeda, so a very local galaxy, and you actually placed it a couple of billion light years away, you shouldn't actually be able to see it with the Hubble Space Telescope because they're too extended, they're too faint, and we wouldn't be able to see them. But astronomers have this really wonderful thing we do, which is we actually really just fundamentally, there's so many things about the universe that we're hoping will surprise us. And so I really love this quote actually from Edwin Hubble himself at the opening of the Hale 200-inch telescope at Palomar, where some reporter was like, hey, what do you want to actually see with this brand new telescope? And Hubble said, I really hope to find something that we hadn't expected. And this is something that astronomers do all the time. We start looking for things that we hadn't expected just because we don't actually know what's out there in the night sky. And so this is what we did with Hubble. Even though we thought we wouldn't be able to see any galaxies beyond the distant universe, we decided, for a completely insane reason, to take this brand new, shiny tool and instead of doing useful science where we knew the answer that we were going to get in advance, instead, what we would do is stare at a very tiny, very blank patch of sky for 10 days. Right? Because that's like a totally normal thing to do with your brand new instrument, where the time is counted in like 1 hour increments. So they spent 10 whole days staring at this patch of sky that's about this size compared to the full moon, so absolutely, absolutely tiny on the night sky. And the thing that they were expecting, if these distant galaxies look anything like the ones around us, is that they were expecting a couple of very faint stars. Because they picked this patch of sky specifically because there was a couple of really, really faint stars in it so that they could tell if they just forgot to like open the shutter of the camera or something, they would still get some stars. And then they downloaded the data, and it turns out it wasn't just stars, it was this whole landscape of these galaxies. So every object except those 2 stars that I highlighted, every single object in this image is a distant galaxy. And most of these galaxies are from when the universe was half its current age or younger. And so the idea is that we can directly observe these distant galaxies and try and use them as tools to actually piece together the formation and evolution of the universe. Right? So every single one of these little objects is a different little tiny dinosaur that we're catching in a different point in its evolution. And we can hope to piece together some sort of story about why they grow and change and how they evolve over cosmic time. But unfortunately, even with Hubble, this amazing instrument that gave us these amazing deep field images, we're fundamentally limited because Hubble can't see very far into the infrared. And so when I was telling you this stuff about cosmological redshift, I left out an important point, which is that along the way from these distant objects to us, the light actually gets stretched. And so the light that's emitted from a galaxy that's very close by, that takes a short time to get to us, doesn't get stretched very much. But if we're looking at the light from very distant objects, it turns out like space-time is actually expanding as this light is flying from these distant objects to us. And so the light itself gets stretched. And when the wavelength of the light is longer, it appears redder. And so if we want to look at these very distant objects, we have to look at redder wavelengths than we would if they were very close by. So if we're sitting here and we're trying to look at this galaxy, which is something like 7 billion light years away, we're seeing that galaxy as it was something like 7 billion light years ago, which is awesome. And if we want to see light that was emitted in the ultraviolet part of the spectrum, we have to look in the visible part of the spectrum. And this is fine because Hubble can see invisible light. All of us can see invisible light. But if we instead want to look at a galaxy that's 11 billion light years away, so much closer to the beginning of the universe, which is 13 and a bit billion years old, we're seeing as it was 11 billion years ago, but we have to look in the infrared to see light that was emitted in the ultraviolet because that light was stretched a really, really big distance in its travels from this distant galaxy to us. And so we have a time machine. We still have a really awesome time machine, but it is a time machine with an asterisk. And that asterisk is that the further back in time we want to look, the redder the light that we actually have to observe. And so, unfortunately, that means that we want to see in the infrared, and we can't do it with Hubble. Because Hubble, the reddest filter that they have on board Hubble is at 1.6 microns, which is in the near infrared. And so this is just, casually a history of the whole entire universe, right? So from the Big Bang through the cosmic dark ages, the formation of the first stars, the first galaxies, all the way to these sort of modern galaxies, and then our very local universe way up here. And this time axis maps directly onto a wavelength axis of like the wavelength that we have to look in order to see those objects. And so because Hubble can only see into the near infrared, it can really only see these modern galaxies. We can't see the formation of the first galaxies, and we certainly couldn't see the formation of the first stars. And so fundamentally, this is the reason that we built the James Webb Space Telescope. With JWST, we can see all the way out to 20 or so microns pretty easily, so way into the far infrared, and we can see the formation of the first galaxies, and we can have an argument after whether or not we've seen the formation of the first stars. I don't think so. I also don't think we will, but other people will give you different answers on that. The other reason that we want to be able to see into the infrared is that different colors of light give us different information about the objects that we're looking at. So, for example, if you looked at these zoo critters in visible light, you can make a couple of inferences, right? You can see these guys are fuzzy and they probably won't kill me, and this guy looks much scarier, right? But if you add in infrared light, suddenly you get a whole piece of information that you weren't able to get just from looking in the visible, which is that these things are warm-blooded and this guy is cold-blooded. And we can do the same exact thing with galaxies. By looking at different wavelengths of light, we can actually get different information about what's going on inside of these objects. And so, as an example, this is the Pillars of Creation. I don't know if anybody else had this as like a poster on their wall when they were a kid. I'm seeing it like at least 3 nods, right? This is like one of the single most classic pictures that we had from the Hubble Space Telescope. So this is a star-forming nebula. This invisible light, we're seeing stars that are forming inside this very dense cocoon of gas and dust. So you can see a couple of very bright stars shining through, but this is all of this gas and dust that's forming new stars. If you look instead at longer wavelengths in the near infrared, all of a sudden you see a very different picture, which is you see a lot more stars, right? So all of these places here that are completely obscured, all of a sudden when you look at longer wavelengths, you can start seeing a bunch of stars there. And you can see everything but the densest, through everything but the densest dust. And if you go even further into the far infrared, this picture is from the Spitzer Space Telescope. This was the absolute state of the art before JWST. This picture is incredible. It's very fuzzy. It's pink. You can learn so much about the dust, right? Totally. So because it's almost Halloween and they made this picture in false color for Halloween, I will preview the JWST image of the same exact field, which is instead this. Yes, thank you, the oohs and ahs, I'm appreciating it, right? So all of a sudden, actually when you go into the mid and far infrared, what you're seeing is actually the dust itself glowing. So you can see this emission from the dust in the background and the dust in the foreground that they've colored so beautifully for us. So obviously JWST is amazing. I kind of gave away the punchline in that the thing worked, but now I will tell you how crazy a journey it was to get there. So we actually started planning. Astronomers have to plan a really long time in advance because stuff is really expensive and it takes a long time to launch into space. And so planning for what was then called the Next Generation Space Telescope actually started in 1989, which was before Hubble even was launched. We knew that we wanted to be able to look into the infrared, so we knew that we should start planning for this next observatory. And it turns out that this instrument is the most expensive, most complex observatory that humans have ever built. It took something like 20 years for us to build it. And the reason is because it's really complicated and we were doing a lot of stuff that was really, really new. And so it has a segmented mirror. So it's about a 6-ish meter diameter mirror. So you can see that's like a normal sized human. And this is the JWST mirror. So it's segmented into all of these different little hexagons. And so that's so that we can get a lot of collecting area and we can see very faint objects. We also want to be able to see into the infrared, and it turns out the sun is like hot. I don't know, crazy, right? And so we have to protect the telescope from the sun, and we do that with this actually tennis court sized sun shield that's made of all these little thin layers of sort of mylar-y stuff. And then it turns out you can't actually launch an entire tennis court into space, and so we folded the whole thing up and stuck it in a rocket, launched it into space, and then hoped desperately that it would unfold the way that we wanted it to. when there was 139 different actuators and 8 different motors that all had to deploy exactly perfectly. And as people who are at Tinkermill, I think you know the challenge of getting things to work perfectly with no oversight. So this is why the thing took 20 years. And then also, like, as if all of that wasn't enough, it turns out the Earth and the sun are both very bright in the infrared. And so why don't we also just put it like 1 million miles away from the Earth? So it's very complicated. Finally, the thing launched. It launched actually on Christmas morning of 2021. It was like 4 a.m. local time. I was at my sister's house in Seattle, and I was like watching the launch in bed with no lights on, so that if it like blew up on launch, I could just close the laptop and hope it was all a bad dream. But it turned out that the launch actually went phenomenally well. So this is the last view, like actual sort of camera image that we'll ever have of the James Webb Space Telescope. So this is a camera that's like on the secondary stage of the rocket, like watching the telescope sort of, you know, it looks slow, but it's actually very fast, sort of fly away from us. And it turned out that they nailed the launch parameters so well that the original mission lifetime of JWST was supposed to be 5 years, which was limited by fuel, because basically you have to get the thing to its orbit, and then you have to spend fuel like turning, looking at the things that all the astronomers want to look at, and keeping it in the right orbit and all of that. So it was limited by fuel, but they nailed the launch so perfectly, like way, way below the specs, that we had to use way less fuel than we thought getting to JWST's orbit point. And so we actually have something like 15 to 20 years of fuel. And so we could theoretically use the telescope that long. I will say that after the 5-year mission lifetime, which is next year, the project scientist does have to go in front of Congress and like ask for more money to keep it running. So we're all like very much fingers crossed that that goes okay, because we will have satisfied the prime mission of JWST, which is 5 years to characterize the entire, you know, early cosmos, which we have not yet done. So, like I said, it's in orbit 1 million miles away. So just to give you a sense of scale, like Hubble is like right in near Earth orbit. When it was broken, when we originally launched it, we could go fix it. We couldn't do that with JWST. It's way past the moon. So that's where it's sitting. We get data from it about twice a day using the Deep Space Network. It like beams data back to us, which is really fun. So after that, we had about 6 months of commissioning, which is where they like align the mirrors, test all the instruments, do all the cool stuff to make sure the telescope does what it was supposed to do. And so I'm about to show you the very first picture that anybody who is an astronomer saw from the JWST, unless they were on the commissioning team, in which case they were getting like 1 million Slack messages from me and all of my friends being like, Christina, is it working? Like, is it okay? And they're like not allowed to say anything because of, I don't know, weird rules. And so they had to be like, just wait, just wait. And we saw this image. So this is the previous best image we had of this star. This is from the WISE satellite at about 3 or 4 microns. This is a really good image, like by these standards. Like WISE was like a factor of 10 better than anything that came before it. But as soon as I fade to the JWST image, you'll understand why I was like, oh my God, maybe I actually have a career in astronomy, right? So you can see that star at the center, like fade into this tiny point source. So this like 6-pointed thing, these are diffraction spikes. It's 6-pointed because of the like all the hexagons in JWST and the mirrors and the struts and stuff. And then you can see all of these like faint objects out here all of a sudden turn into like actual shapes instead of fuzzy blobs. So it's the first time we were ever able to actually resolve these distant galaxies. And then, probably most excitingly, is all this like tiny stuff that like pops out of the noise that we didn't ever see at these wavelengths that all of a sudden we're seeing at like very, very high significance. And so as soon as we saw this image, we were all extremely, extremely excited. And so with that, I want to tell you a couple of like early science results. So I sort of geared us up for talking about the very first galaxies. And so again, like we launched this telescope in large part so that we could observe these galaxies that are just 300 or 400 million years after the Big Bang, where we have to look into the sort of near and mid infrared in order to see any light from these galaxies at all. And so our expectation was that we were probably going to find a couple, Like we were probably going to find a couple of really early galaxies that were very faint and probably look very different than local galaxies. So this that I'm showing here is a movie from a simulation that just includes dark matter of how we think our universe evolves. And so we start out, I'll actually play this again. So we start out with just this very close to uniform field of dark matter, and then all you do is turn gravity on and let stuff fall. And things will tend to collapse. And so you see as time goes on, this is decreasing in redshift, so as time gets later and later, you start to see all of these collapsed structures. And so this is where galaxies live. Galaxies live at the middle of these sort of dark matter filaments where all of this stuff has had time to fall in and condense into something other than just like fuzz. And so if you look in the very early universe, this process hasn't had that much time to happen. And so we think that galaxies shouldn't be that big. And so if you were to look at for example, the maximum mass of any galaxy in your field of view as a function of time, you would expect that it should increase with time. It's not exactly a straight line. I just sort of simplified some things, as you can see from the XKCD plot. Which you have to install fonts for in order to make this work. That was my adventure today. I was making this one plot, so I hope you love it. It's a line. So basically, you should see things that are more and more massive the later you go in time. And instead, well, here, I'll first show you. So this was the whole state of the field before we got JWST. And so this is the brightness of distant galaxies as a function of how far away they are. So this is redshift. And so there was a decent number of candidate galaxies up to what we call the epoch of reionization at about redshift 8. And then there's this one dude sitting at redshift 11 called GNZ11 that my friend Pascal found in the 2000s, and it was a huge deal. It's still actually one of the brightest distant galaxies that we've ever found because we look at the same very small patches of sky. And so we started getting all this data from JWST, and we were this is the point of its mission is to find these distant galaxies, but we think they're going to be really rare because there hasn't been that much time. And then we got the very first extragalactic image that they took with the telescope, which is called the SEERS program, in June or July of 2022. And we were looking at the data, and immediately, my friend Rohan found 2 extremely distant galaxies, one of which was already in literally the first picture that we took that was supposed to be looking for galaxies, already the most distant object that we had ever found. And then it turned out that we were not just lucky. People just kept finding more and more and more and more of these things. So I sort of jerry-rigged, this is now an entirely new axis where we're going way out until now the most distant confirmed galaxy is at redshift 14, which is just 280 million years after the Big Bang. And so it turns out that there's actually maybe too many of these distant galaxies. Maybe we were too successful at this mission of finding these very distant galaxies. Because if you compare the number of distant galaxies that we found, sorry, this is an actual plot from a paper that I didn't annotate very well, but here we have the number of galaxies as a function of redshift, which is the distance they are away from us. All these colored lines are models for what we thought we should see before the telescope launched, and then this gray band is what we've actually observed. And so there's 1, maybe 2 models that are sort of able to predict this, but in general, all of the models that we had for how the universe evolves were falling short of the actual number of these bright distant galaxies that we found by a factor of 5 or something. So this is actually we don't know why this is still. People are still trying to figure out why there are so many bright distant galaxies. And so one sort of explanation for this is that maybe stars in the early universe are forming very differently than stars in the local one. And so this is another movie from a simulation about how stars form. And the colors are just different temperatures of gas. And the thing that I want you to focus on is that there's all these times that it goes boom, right? So all of this gas sort of expands and then it falls back down. And so maybe if this star formation is really, really bursty and really stochastic, and we have all of these times where There's this giant starburst that explodes all of this gas that makes the galaxy much brighter. And so for some reason, we're just seeing more bright galaxies because something is very different about the way that stars are forming in the distant universe. So this is like one type of thing that we knew that we should look for with the JWST. It is not the only type of thing that we knew that we should look for. And so I will tell you about a different type of dinosaur that we thought we should look for, which is things that are red. And so there are things that are red because they're very far away, which is these early galaxies I was just telling you about. And then there are things that are red because they're just intrinsically red, which means probably they have a lot of dust obscuring all of the light in the visible. And so it turns out that being able to peer through that dust lets us see entire populations of galaxies that we had never seen before. So this is an image from the Hubble Space Telescope, and I will blink to the same exact location in the sky with JWST. And all of a sudden, there's this giant red thing, right? That was just completely and totally not there with Hubble. So we had never seen this galaxy before. And we knew that we were missing galaxies because you can see them in the very, very long wavelengths, like you can see them if you look with radio telescopes. But radio telescopes aren't able to actually resolve these, and you don't know anything about the properties because you basically just see like there's a radio source and it's really faint and I know nothing else about it other than it's probably a galaxy. Whereas now we're able to see this thing in many different wavelengths and characterize the physics of it. And so we actually found this. This was a paper that was led by my coworker at CU, Erica Nelson. And so we started looking for these things, and it turns out there's a lot of them. So this is like what a normal galaxy looks like. This is sort of a bluish spiral galaxy like our Milky Way. And these are all of these really red dust-obscured galaxies that we found. This is the same exact color scale. So like these are just really, really red. They're just not there in any other filter. And most of these things are like disks that are, they're not circles, they're ellipses. And so we're looking through like the thick part of the pancake. And so that's why we think they're so, so red. But this is basically the very first time we've ever been able to look at galaxies like this. And it was sort of a systematic bias in our understanding of the population of different galaxies because we were just systematically missing these things that were sort of edge on. And there's, again, more of them than we thought that there would be. But while we were looking for these, so we were sitting at the Rayback. This was like a couple summers ago. It was Erica and our friend Rachel and I. And Erica was making this color selection to look for these red galaxies. Rachel was trying to fit their properties. So she was fitting a complicated model to try and figure out how massive they are and how far away they are. And I was fitting their sizes. And all of a sudden, we realized that we found some really weird things because not all of them were these big inclined disks. Some of them were instead these extremely boring looking little red dots. But it turns out these little red dots are actually really cool. So when Rachel fit for their masses, it turns out that they are very distant and very massive. And so this is the mass of a galaxy. So if you were to weigh it, how much it weighs, as a function of redshift, how far away it was. And so this population that we found turns out to be pretty close to the mass of the Milky Way. These are like already up to half the mass of the Milky Way, but we're finding them like less than 5% of the Milky Way's age. So basically, we're sitting there like at the Rayback thinking that we're looking for these tiny baby galaxies that look very different from anything we've ever found before. And we're looking at the right time, but instead of finding an itty bitty little baby galaxy, we find like the Milky Way. This is like very distressing. We're like, what have we done? What's wrong? Something bad has happened. Like this is not what the universe is supposed to be like, right? And so this would imply that galaxy formation began much, much earlier and happened much, much faster than we had originally thought. And so this was like a very fast turnaround area of astronomy. This is like we just got the first images. And so it was like I don't know, the Rayback was closing, we wanted to go to sleep. And so instead, I'm not sponsored by them. I don't know why I said the name of the place we were like 5 times, I promise. But anyways, we wanted to go to sleep, so we sent them to our friend Evo, who's in Australia. And we woke up to like truly like 50 Slack messages just from Evo talking to himself throughout the middle of our night. That was like, guys, I found more. Guys, they're really massive. Guys, this is bad. And so anyways, like 3 days later, we published a Nature paper. So that was really fun. That was extremely fast turnaround. And a day after that, our friend Mike Boylan-Colchin basically made that XKCD plot that I just showed you of like the mass of a galaxy over time, what you should expect. He made that, but like with actual things, not with just XKCD. So like, don't really worry about the axes. This is basically showing like the mass of the density of sort of objects that you can expect as a function of their mass. The thing to focus on is that this blue area, this has more stellar mass than all available baryons. So baryons includes like stars and gas and dust and dark matter and lots of different things. And it turns out that galaxies are like normally really inefficient at forming all of this stuff into stars. And so like normal galaxies are like here in this plot, like well below this gray curve. And these points are like, distressingly, this area goes into the like disallowed by all of our physical models part of the plot. This kind of turned into a big thing because Mike told the universe that we maybe broke it, right? This was like sort of the title of his paper. And so there was like a million news articles, and Neil deGrasse Tyson was on CNN. This is Erica on 60 Minutes. This is like my science grandpa Peter on CNN. It was like kind of a lot for a few weeks. Like everybody was like, oh my God, you guys broke the universe. These objects are absolutely insane. I do want to say like we didn't actually break the universe, but we were very careful to say that these objects, if all of our models are true, we've looked at all of the possible ways that we knew about before this telescope in order to explain these objects. And the only way with those models we can explain them is if they were extremely, extremely massive and extremely, extremely early. And it turns out we just didn't have the right models for these objects. And so I want to take a brief digression into like how astronomers actually like do this kind of modeling, which I know is like a little bit in the weeds, but it is most of what I do, so I figured I would talk about it. So the way that we normally do this is we take images at a bunch of different wavelengths. So this is like a nearby galaxy. And then you plunk an aperture down over the galaxy and you sum up all of the light. So you turn each one of these beautiful pictures, or in the case of the little red dots, like a tiny little dot, you turn it into a single point on this diagram, which is called a spectral energy distribution. And so this is showing how bright an object is as a function of wavelength. And so these 6 images turn into these 6 data points, and then we fit a model to it. And this model is very complicated. It's very bumpy. It encodes everything we think we know about how stars form and evolve, and they're basically they emit light, and that light is reprocessed by the effects of dust. And there's like probably like 100 free parameters in most of these models that you're fitting to 6 data points. So like I live in a kind of scary universe in that sense. And so the point that I wanted to make with this is that sometimes there is more than one line that you can draw that will go through these 6 data points. And this is what turned out to be the case with these little red dots, is that there was a model that we didn't know that we should have because we had never seen any type of object like this before. And so the way to actually like sort of break this degeneracy of only having 6 data points and having a really complicated model is that instead you take a different type of data. So instead of taking imaging data, you take what's called spectroscopy. So basically you take the light and you put it through a prism and you disperse the light into all these little different bits of the rainbow, and then you ask how bright is each little bit of the rainbow. And so then instead of 6 points on this diagram, you get basically a continuous line. And this actually is a spectrum of one of those first little red dots that we found. This is not a galaxy. We still actually don't know what it is. We think maybe it's a supermassive black hole. We think that probably because these lines are really broad. These lines are like thousands of kilometers per second that this gas is moving. And we don't know of anything else that can do that other than a black hole because their gravity is so, so intense. And so it turns out these things are like absolutely everywhere. These are like some of the most numerous objects in the distant universe. And they're all just these little red dots. That's like their actual name. Like I'm not just calling them that. Like people have now shortened it to LRDs. So if people ever talk to you about LRDs, it's little red dots. You have to be very careful what you say in astronomy because somebody will make it into an acronym and it will be bad and it will haunt you forever. And so like our current best guess about what these things are is that it's a totally new phase of supermassive black hole evolution called a quasi-star or a black hole star, where you have this like crazy supermassive star that formed very early in the universe, and then it collapsed and formed a black hole, but it still has all of this really crazy dense gas around it that's emitting, and it's not a phase that we have ever seen before in the local universe. And so these objects are like totally and completely new, and they're one of the most like fun things that we've discovered with JWST. And again, we like actually still don't know what they are. Like I pulled this cartoon from like a paper that a friend of mine wrote because I was like, I don't know, Mitch, you might be right. But like we still don't actually know. Like our original paper, I think, has like, there's now been like 600 papers on, like of astronomers. There's not that many astronomers, right? And so like there being 600 papers means like this is the thing that people are like most interested in for whatever reason. I guess the reason is that they're like the most unexpected thing so far. And then I want to talk like just a little bit about what's next. So this has just been a couple of years of JWST data, and I've just shown you like a couple of results. So I'm going to flash a bunch of other things in our last couple of minutes here. So a lot of what I spend my time working on is the Uncover survey. There's a couple of little red dots. I don't think you can see them. This zoomed out. There's one right there. So it turns out this is a lensing cluster. So this is it's called Pandora's cluster. All of these galaxies that look white are at the same redshift. This is actually one of the most massive clusters at this redshift. And it's so massive that it's actually bending the light from all the galaxies around it into these like crazy like little bananas, like all of these arcs, faint arcs. And so you can see much fainter, intrinsically fainter galaxies than you would otherwise. So we stared at this field for a really long time. And the thing that I have mostly been spending my time doing is, like I said, this sort of diagram of our flux density versus wavelength. It's really annoying to try and fit a very complicated model to 6 data points. So most of the science I've been doing right now has, instead of taking 6 data points, to fill this in and take all of the other 20, they're called medium band filters, that are on board the telescope. And so the survey that I've been running is called Medium Bands Mega Science. If you guys have seen me, like I learned how to do embroidery so that I could like embroider our logo on hats for everybody. So if I was like in the textiles room, like this is what I was doing. And so basically we're able to look at these galaxies in a bunch of different wavelengths. So just to show you briefly what this looks like, this is a galaxy. It's maybe not as beautiful as those Hubble ones, but it's also like 3 times further away, so I feel good about it. So this galaxy, if we step through wavelength, you see all of a sudden you just see these little clumps that get really bright, and then they get faint, and then they sort of are bright again, and then they're not there, and the main galaxy is just there. And so it turns out that basically all of those times those little clumps are going up and down in flux is because we're going across these little spiky things in the model. And if you, I don't know if there's any chemists here, but these are like transitions of the hydrogen atom mostly. So this is like a quantum thing where the electron can either, whatever, it can be in the n=2 state or the n=3 state. Anyways, it's fun. And so like we can take these really pretty images where the sort of point of this is that these are all different wavelengths. So this is the imaging that everybody else has taken in the broadbands, and these are the new images that my team has been taking, where you can see all these little bitty clumps lighting up in these different colors. That's because we're probing these different strong emission lines. And so most of what I've been doing is looking at these sort of multi-wavelength morphologies of all of these distant galaxies and trying to understand their spatially resolved structure. So basically to move beyond the thing that I was showing where you're treating these galaxies like you're reducing all of the data down to a single point, instead look as a function of where you are in the galaxy and try and understand their properties that way. And so you can do a lot of cool things with that. So one of my grad students is using this to map star formation and dust in distant galaxies. So this is like a really beautiful spiral galaxy. And this is not just an image. This is actually an image that Brian has processed. So this is just where the older stars live in the galaxy. And this image is just where the new stars are forming. So you can see that like the new stars are forming all at the center, and then you can see the spiral arms really clearly highlighted. And so you can look at where, like how galaxies form stars in this really cool spatially resolved way. My student Natalia is finding the most extreme sites of star formation in the universe. So she's finding these objects that are really, really, really bright in some filters and then like not there at all in other filters. And this is because they have very, very strong emission lines and probably some really weird physics that's driving it. My postdoc Icky is finding totally new classes of distant galaxies. So he's finding these galaxies that we never would have thought were very far away when we only had 6 data points. And now that we have 20 data points, it looks like they're actually much further away than we would think. And then also we're looking for all these little satellite galaxies. So like you guys identified the Magellanic Clouds at the very beginning. So the Magellanic Clouds are satellite galaxies of the Milky Way. So they're smaller galaxies that are orbiting around us. And we're now able, for the very first time, to see those satellite galaxies when the universe was half or a third of its current age. And we're able to count them up and try and understand how these satellite populations evolved into the ones like we see around the Milky Way today, which is really fun. So my student Jenny is working on that. And if all of that science that I told you in not a lot of detail sounds really cool, there's good news, because this is all from this sort of medium bands mega science program, which is about 30 square arc minutes on the night sky. And currently, we are taking data from another program that I'm co-leading, where we are instead getting that same medium band imaging data over this much of the sky. And so basically, this winter, I will be embroidering this logo on hats instead. And so this is a really, really exciting program. I'm super stoked about it. If I've seemed stressed and distant lately, it's because we got this chunk of data over this part of the field. So we got about the first 25 hours out of 270 of our data. And so we've been already finding a lot of really new and exciting things in that data, and there's a lot more to come. So it's like 10x the area that we've taken before with this kind of stuff. And the thing that I'm honestly most excited about with this survey is continuing to do this thing of looking for things that we hadn't expected and trying to find all of the weird new things in the data now that we're able to look at a much larger area of the sky. So that's all I have for you tonight, but I'm happy to take any questions that folks have.